Ready to Algebra 2, Section 9.4, Mutually Exclusive and Overlapping Events. So mutually exclusive or disjoint events are events that can't occur in the same trial of an event, aka they can't occur simultaneously or at the same time. So it might be said that the probability of A or B, let's say event A happening or event B happening, is just equal to the probability of those events individually. Whereas we have overlapping events are events that have one or more outcomes in common. You could say that they can, but not necessarily have to happen at the same time. So here you'd say the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And we'll get into the probability parts in a moment. So example 1, we're going to determine if these are mutually exclusive or overlapping. So Sarah draws a single card from her deck. The card is a king or a red card. So the question is can the card be the king and a red card? If it can be both, then it is overlapping. If it only can be one or the other, there's no like red kings, for example, then it's mutually exclusive. There are red kings in the deck, 2 of them to be exact. So these are overlapping events. They could both occur at the same time, but it's also possible that you just get a red card that's not a king, or a king that's not red. Sarah draws the singular card from her regular deck. The card is a jack or a queen. So can that happen at the same time? Can the card be both a jack and a queen? Nope. So these are mutually exclusive. Go ahead and try letter C on your own. Jane rolls a 1, 2, or 3, or an even on a die. So that's overlapping because 2 is an outcome that they both have in common. Because the first event, A, has it rolling a 1, 2, or 3. The second event, B, has it rolling an even 2, 4, or 6. So they have one event in common at least. Example 2, we're going to use this Venn diagram to help us. A numbered dodecahedron has 12 sides numbered 1 through 12, aka a 12-sided die. What's the probability that you roll an even or a 7? Let A be the event that you roll an even number. So A is even, and B be the event that you roll a 7. So let S be the sample space. So these are all the potential outcomes. So complete the diagram by writing all the outcomes of the sample space in the appropriate region. So over here we'll put 7. It's the only number that fits that description. And I probably should put 7 in here, and I should probably put even in here. And the even number is 2, 4, 6, and it's 12-sided. So 8, 10, and 12. And there's no overlap, so we just leave that blank. But if there were any evens that were 7, we put them there. And then our other numbers in the sample space, we have 1, 2, 3, so not 2, 3, 5, 9, and 11 that are not a part of outcome A or event B. They are not even and they're not 7, but they are still possible outcomes on the die. So we can use this to visually help us see the probability of event A happening, the probability of it being even. So we see here there's 6 options out of the 12. So 6 over 12 is the same thing as 1 over 2. So it's going to happen half the time, or should. Then we have what's the probability that you get a 7. Well, it's 1 out of the 12 sides. We can only see there's one option there and the 12 total ones. And the probability to get A or B, since these are mutually exclusive, all you do is add all these options up and say, okay, well, 7 fit those out of the 12. And once again, you would have arrived at that 7 over 12 by doing 6 over 12 plus 1 over 12, getting 7 over 12. Next one, if you were to roll the dodecahedron again, dodecahedron, put a word emphasis on it, what's the probability that you roll an even number or a number greater than 7? So these are the even ones, and these are the ones that are greater than 7. So even numbers 2, 4, and 6. Evens that are greater than 7 will go in this category because they fit both. That's 8, 10, and 12. And numbers that are just greater than 7 but not even are 9 and 11. And then other numbers that don't fit either of these events but are still potential outcomes in the sample space are 1, 3, 5, and 7 because 7 is not greater than 7. So the probability of event A happening, the probability of getting an even, is all of these. So you have to look at the whole big circle. So you have 6 out of 12, which is 1/2. Probability of event B happening is all of these, 5 out of 12, and that doesn't reduce. The probability of event A or B, on this one, we cannot just add 6 over 12 and 5 over 12, because that would give us 11 over 12, and if there's 4 of them that don't fit either one of those, then it can't be 11 over 12. So what we have to do is we have to subtract our overlap, which is 3 numbers out of the 12 options, 3 outcomes overlapping. So you take 11 over 12 and get 8 over 12. That's what this was talking about earlier, that when they're overlapping events, which these are, there is overlap as we saw in our Venn diagram, you have to add the 2 probabilities of the events and then subtract the probability that of the overlap, where they both occur at the same time. So 8 over 12, which reduces to 2/3. Now, if you have the Venn diagram, if you have it drawn out, it's a little bit easier to do it another way as well, where it might not be as easy if you don't have it drawn out. That you can visually count 1, 2, 3, 4, 5, 6, 7, 8 options out of the 12 and just get 8 over 12 that way. But if you don't have this drawn out, it can be hard to think in the moment, okay, wait, so how many are there total? And then just get the number 8 in this scenario. So a lot of times we rely on adding the 2 individual events and then subtracting our overlap. On to the next page. Additional rule for probability of overlapping events. So this was exactly what we just talked about a moment ago. So that's the probability of A, or B is equal to the probability of A plus the probability of B minus the probability of A and B happening, the overlap. So we already did that. And then I want to note that, hey, if they're mutually exclusive, like we were just talking about on example, I think it was 2. We have example 2. If they're mutually exclusive, then the probability of A and B happening at the same time is non-existent, it's 0. So it's like you could have taken this one and subtracted 0 over 12 because they're mutually exclusive and gotten the same answer, 7 over 12. So if you want, you can always just rely on the same rule, so to speak, of following this pattern, and then just subtracting 0 when they're mutually exclusive and have no overlap, or thus have no overlap. So example 4, probability of A is 1/3, probability of B is 2/5, and the probability of A and B happening at the same time is 1/5. So find the probability of one of them happening. So we're going to follow this pattern. So probability of A or B is going to equal 1/3 the probability of A plus 2/5 the probability of B minus 1/5 the probability that they happen at the same time. So here we're going to want to get common denominators. Our common denominator is going to be 15. So we're going to have 5 fifteenths plus 6 fifteenths minus 3 fifteenths. And that's going to land us with 8 over 15, which does not reduce. So once again, we just follow the same pattern we did earlier. This time we were just given numbers compared to example 3 where we found them from the Venn diagram. And then this time we also had to get common denominators. Example 5, probability of A. We know the probability of A or B, and A and B. We don't know the probability of B. So we follow the same pattern, but we just fill in something different. So we said probability of A or B equal the rest. So it's 2 over 5 equals probability of A, 3 over 10, plus the probability of B, which we don't know, minus the probability that they happen simultaneously, which we said is 0 right here. So really all you need to do here is subtract 3/10 and get a common denominator. So 2/5 and 3/10. And the common denominator is going to be 10, so you're going to have 4 over 10 minus 3 over 10 will give us the probability of B. And that'll tell us the probability of B ends up being 1 out of 10. All right, example 6. A card's randomly drawn from a standard deck of cards. What's the probability that it's a 5 or a jack? So we got to figure out, hey, is this mutually exclusive or overlapping? And this is, in fact, mutually exclusive. Good to note. So probability of the or happening, probability of a 5 or a jack is equal to the probability of a 5. There are 4 5s in a deck of 52 cards. Probability of a jack, 4 jacks in a deck of 52 cards, and there's 0 overlap. Because you can't have both, so you don't even need to put the minus 0 over 52 if you don't want. And you get 8 over 52, which reduces to 2 over 13. Because you would reduce the top and the bottom by 4. What's the probability that it's an ace or a heart? So these are overlapping events because there's an ace of hearts. So the probability that it's an ace or a heart, you could write out, you could put a little H for a heart, or I just drew a little heart. Probability that it's an ace, there's 4 of them, and there's 13 hearts. You need to subtract the overlap, which is the ace of heart itself, the one card, and you would get 16 over 52, which reduces to 4 over 13. Go and try letter C on your own. So C, these are overlapping again because there are 2 red queens. So the probability that you get a queen or you get a card that's red is 4 over 52 because there's 4 queens, plus 26 red cards, half the deck, minus the overlap, 2 of the queens being red. And you'd end up getting 28 over 52, which ends up reducing to 7 over 13. Example 7. Of 100 students surveyed, 92 own either a car or a computer. Also, 65 own cars and 82 own computers. What's the probability that a randomly selected student owns both? So, the probability of a car or a computer would be equal to the probability of owning a car plus the probability of owning a computer minus the probability of owning both. So we plug in what we know and solve for what we don't. So we know that 92 out of the 100 own both. We know the people that own a car are 65. We know 85 own a computer. And we're trying to solve for those that own both. Or you can put car plus computer. Car and computer if you want. So here we need to get this by itself. So we can add these together and get 92 over 100 equals 150 over 100 minus the probability of both. Continuing, we can subtract 150 from each side and get negative 58 over 100 is equal to the negative probability of both. So really then we just need to divide both sides by -1, or multiply both sides by -1, which just makes them both positive. And so the probability they own both a car and a computer is 58 over 100, which is 58%. I mistook my math there for a second. What did I do wrong here? Oh, I put 85 instead of 82. My apologies there. Let me fix that. 82 own both, which makes this 147, which makes this 55 here, which would make this 55 over 100 that own both, aka 11 over 20 if you reduce. Or, like I said, 55%. So I apologize on that. I wrote down 85 the whole time instead of 85, which would throw off my math by 3 each time. So each student cast one vote for senior class president. Of the students, 25% voted for yours truly, 20% voted for Mr. Titus, and 55% voted for Mrs. Springer. What's the probability that a student voted for Springer or Titus? You know, I feel like I got gypped in this vote, but that's okay. So here, you might notice a shortcut right away. If you do, great. If not, we'll get there. So the probability that someone voted for Mrs. Springer is 55%. Probability that they voted for Coach Titus is 20%. And could they vote for multiple people? No, they could not. So there's no overlap. And that would end up landing with 75%. And you could just add those two right away. And that would have been much quicker. So our last example for this section, find the probability that someone is a senior or a non-athlete. So here we have a table. Here's all the seniors, including those are athletes, non-eats, and then just non-athletes, non-eats, and then the total number of seniors. So the probability that there's that they're one or the other, you would take, and I'm going to do probability of S or NA for non-athlete and senior, and get 202 for the over 808. I need to put that over 808, my apologies, because that's the total number of students, plus the non-athletes, which the total number of non-athletes in all grades is 412 out of 808, and this is obviously just some random sample. And subtract the overlap, the non-athletes that are seniors, 108 over 808. And if we combine all those, we end up getting 253 and reducing over 404. So if you didn't reduce, it would be 506 over 808, which reduces to 253 over 404, by the way. And if you wanted, here, since you have a table, oh, pardon me, that would not have worked. My apologies. I was going to say something we could do, but I recognize I was making a mistake mentally there. So we follow the same pattern we do before. We take the seniors, and there's 808 students. The non-athletes, 412, divided by the 812 total students, and subtract the overlap of 108 seniors that are non-athletes away from that. So then if you wanted to put this in a percentage, which you don't have to, but you could, would be 63%. Once again, just like on the others, minus this one where it's given to us in percent, you could just leave it as a fraction. All right, that is it for section 9.4.